So here we are going to understand the practical significance of logarithmic decrement delta over the damping factor zeta. It is one of the questions that has been asked in the DADO interview. So let's discuss this. First of all, in order to understand the practical significance of the logarithmic decrement delta, first over the damping factor zeta, first let's understand what is the problem. Suppose this is a cantilever beam. Okay, so if you design a beam, let's suppose for jumping into the swimming pool. Some people are jump over here in the swimming pool. Now after they are jumping, you have to design this cantilever beam in such a way that after getting the disturbance, this will be vibrate, or this will have the motion like this. So you have to design this system in such a way that after getting this initial disturbance, it should become in the mean equilibrium position in much quicker manner. So in order to design this cantilever beam, for this case you have to must know the damping parameter of the system, or you have to must know the damping factor, that is the zeta value. And in order to find this zeta value, we know that zeta is given by C over Cc. C is basically the actual damping coefficient of a system, and Cc is critical damping coefficient, and it is given as 2m omega n. Further we can write this as 2m root over k by m. So in this case we observe that the damping factor zeta is basically depend on the actual damping coefficient of a system C and the system parameter like mass, coefficient, stiffness of the system. So we have seen that the zeta is basically function of C, M and K. So this is very simple system, we can able to determine this. But what about a very complex system? For very complex vibratory system, it is very difficult to determine the actual damping coefficient, mass maybe we can determine, and stiffness. So it is very difficult to determine the parameter damping factor zeta. So here the one useful tool come, that is a logarithmic decrement delta. So it's a very useful tool. This tool will quickly give the damping value of any vibratory system. Let's suppose this vibratory system, if we disturb initially, and how the quickly the vibration will be damping or will decaying, we will assess easily by this tool logarithmic decrement without knowing the system parameter like actual damping coefficient, mass and stiffness. How? Let's look into this. We know that the logarithmic decrement is given as natural log over x1 into x2. x1 and x2 is basically a two consecutive peak displacement after the system getting initial disturbance, and we can able to get this response of the disturbance by using some sensor like accelerometer. We will put accelerometer in this here, and after getting initial disturbance, this accelerometer will capture the response of this initial disturbance. Let's suppose the disturbance capture or response capture is like this one. So here we have seen that this is the maximum displacement. Let's suppose at time t1 here x1, and after time t2 its displacement is x2, and it is decaying like this. Because it is a natural vibration and its vibrates on, so it will be decay. After some time it will come to at equilibrium position. Now we can able to determine the logarithmic decrement delta by simple taking the natural log value of two consecutive displacement x1 and x2. So here after getting this logarithmic decrement, we have one formula like 2 pi zeta 1 minus zeta squared. So after getting this value delta from this response curve, we can easily able to calculate this zeta damping factor, and we know that zeta is basically show that how quickly the initial vibration will decay with the time. So if we are able to get this value, then we will easily able to design the damping behavior of any system. So here it is the practical significance of this logarithmic decrement. We can able to determine the decaying property of any vibrating system without knowing the system parameter like coefficient, damping coefficient, mass and stiffness.